Welcome everybody. This is the Open Source Antibiotics Mur Ligase meeting on Tuesday, the 8th of February. We have some new people joining us. Do you want to do some intros? Just whipping around the screen, is that all right? If that's okay, I can get going. I'm Todd. I'm Professor of Drug Discovery at University College London. I can dictate the order on my screen if that's okay. Julie, I don't think we've met before. Julie, are you able to?
Sorry, it's just somebody came into my room. I work for Chris Dowson in his research group as senior research technician.
All right, great, welcome. Chris, Swain.
Chris Swain, I'm a medicinal chemistry consultant.
And Chris Dowson.
Professor of Microbiology at Warwick.
And then Anita.
A senior research technician working for Chris Dowson.
Hi, welcome. Then Bart.
I am Bart Staker from the Seattle Structural Genomics Center. And then we also will have Jan Abendroth, but he won't be joining us till, I think, 35 or so.
No worries. Okay, Joe.
Joe Eyermann, Northeastern University in Boston, computational chemist.
And then Becca.
I'm a PhD student working with Chris Dowson on the assay side.
I think so. Adrian, first time visit, I think. Nice to meet you.
I'm nice to meet you. So Adrian Lloyd, work with Chris Dowson on Mur Ligases in general and assays and enzymology.
That's an understatement. Adrian is wholly responsible for the whole of that program.
Okay. And then Ed.
Hi, I'm Ed. I'm one of Matt's postdocs here at UCL.
Ed is the new Dana. So Dana has gone and gotten a job in a company elsewhere, so is no longer active on the project. She's still in touch with us and everything. Ed is stepping into her shoes. Welcome, Ed. Zige, you finished your project, but it's great you've come.
Oh yeah, master's student with Professor Matthew and still interested in the project, so keep in touch.
Great. And Shah? You're unmuted. Hello. If you want.
Hello.
Yeah.
Hello. How are you guys?
Yeah, good. You are. We're doing little intros. If you can just say who you are.
Oh, my name is Shah Hamza, master student in the drug discovery course
at UCL. Great. Yuhang, you're next.
Hi everyone. I'm a PhD student with Matt, working on my ligase project.
Okay, and last but not least is Lizbe.
Okay, hello, so I'm Lizbe. I'm in Frank van Delft's group in Oxford. At this moment, I'm actually a diamond, but yes, I'm a crystallographer.
Okay, thanks everybody. That's great. So shall I'll just pop up the agenda so that we all know what we're looking at. And there's lots of things, obviously, to talk about. I don't know if anyone wants to lead off because you've got a presentation that's relevant to what's here already. I don't want to dictate the agenda necessarily. Does anyone want to go first here and present new data that's needed here? I mean, from my perspective, looking at previously the compounds that we sent to Warwick that Dana made that gave apparently inhibition of 2 MERS. And we were at the point, I think, of trying to get dose response data and ultimately trying to get crystallographic data that showed that the compounds were binding in the same area of the protein as the original fragments. I guess for me, that's one of the key things. Did anybody want to talk to that part of things?
I have those dose response curves. I actually tried to email them to Dana this morning and obviously found out she'd moved on by her email response. So I can show those dose response curves now if you'd like to see them.
That would be great.
Yeah, they need to be put up online, but at the moment I'm just trying to figure out the best way to actually show them. But hopefully I can find it for you.
Hi, Jan and Laura. We just gotten started, and Becca's about to show some data.
Yeah, so these were the compounds from Dana, which I tested and showed the dual inhibition against Mur E and Mur D. And so I have now run the dose response curves against Mur D, step A galacticae. And unfortunately, 788 has started precipitating at 37 degrees C, so we can't get a dose response curve for that. But the other 4, which all show dual inhibition, we now have these dose response curves for. And so obviously, as you can see, 759 is looking the most promising from that, and probably would be the one we'd want to look at continuing forward. Otherwise, the other 3 all look roughly similar. The IC50 does vary a little bit, but 759 is definitely giving us the best IC50 in hill slope.
And I mean, it's great. How many? I mean, you're happy with the data in terms of, you know, the lines are generated from a series of points, right? And you're happy with the way they look.
So each line is generated from 8 data points currently. If we wanted to get the full 10, I can run them, but from the 8 with the error bars, we were quite happy that that was giving us the correct curve.
Mm-hmm. I mean, 759 looks fantastic if it's 20 micromolar, a compound that size.
Yeah.
Could you just show the previous slide so I can remember what the structure is?
There you go.
Okay. Yeah, very simple structure.
Yeah.
I mean, these are elaborated fragments, so they are, you know, 3+ heavy atoms heavier than the originals.
Yeah.
So if that 759 is right, that's really great.
And do you know if it's a competitive inhibitor?
I've not done any testing to see if it's competitive or not, no.
Okay.
That can obviously be something we can run if we want to know, or we can wait to see from the XChem and binding to see where it's binding to confirm that.
Yeah.
Well, I will make a comment on that later on when I'm presenting.
Okay.
The conclusion is going to be we're going to need the essays, basically. But I will discuss it later.
Okay. Okay. That's very nice. Fantastic. Have you got any? Anyone got any other comments on those curves? Okay, that's interesting.
So I
mean,
assume you didn't. I didn't see things going up to 100% inhibition. Not a big deal, but it looks like they weren't going fully to 100% inhibition.
No, we didn't go all the way up to 100%, so we were more interested in the actual slope, and so we just did the 1 millimolar, which we started with, and then went to get the lower end. I can increase it, but obviously we then start to have to worry about DMSO concentrations affecting the protein within the assays. Because
yeah, no, that's totally fine. Thank you.
Yeah,
no problems.
That's okay.
For Ed and Kato, it would be interesting to see which compound structurally similar to 759 gave nothing. So just to add to the idea that we're getting a specific interaction. So if you've got the 3-position nitrogen on the pyridine versus the 2 similar compounds which were ineffective, we can learn a lot from that. But that's nice. Okay, fantastic. So I guess, is it, well, it would be useful, I think, to skip to the issues to do with crystallizing those compounds and getting structures bound. Should we discuss that now? Because obviously that would be very nice to be able to do. Laura, did you want to talk about that?
Why not? Let me share my screen.
So you're presenting on the same structures, right?
Yeah, on the same dual inhibitors. Next up. Can you see it?
Yeah.
Yeah.
Right, pen, no. Okay, so I'm gonna skip the SPR part. We can talk about that later. So I tried to crystallize, soak these compounds in E. coli Mur E crystals, and as well as E. coli Mur D crystals. So in the case of Mur E, these are the results. So I incubated them for 1 hour, like we do with the XChem at the same XChem concentration. So everything should be the same, except for how I'm adding the compounds, because this was done manually. This wasn't done in Diamond. And then I observed some of the compounds melted, but not all of them. So the ones that were closer, the closest to where I added the drop with the compound, those were melted, but the rest were not. And then in the case of, I also incubated with ADP, and those melted after like 15 minutes of incubation, they were gone. I included as well the AstraZeneca compound that I got from Yuhang. And yeah, and in the case of so I got a lot of data sets for these compounds. They are all between 2.3 and 3 angstroms resolution. And I couldn't see any compound bound to any of the structures, but I saw a change in the conformation. So, wait a second, I can't see. Yeah, so this is the structure basically. The gray structure is the one, the APO structure that we were always getting this model on the XChem results. And the yellow one is the dual inhibitors structures, like this experiment, and they all look like that. So there is a shift in a more compressed conformation. Now, this might be an indication that there is something binding and is doing something to the structure. So I think it's worth following up on the compounds and trying to see if there is any competition on the with the ATP, for example. Yeah, so that's worth doing. I also set up crystals for co-crystallization, crystal plates for co-crystallization to try to get these crystals in a different way. And yeah, so, but I couldn't confirm the binding with this experiment. And then in the case of, yeah, sorry.
Just a quick question. Is the picture you're showing on the right of the change in the conformation, is it basically the same conformation in each experiment, regardless of the compound? Right.
Yeah.
So, and if that conformation is changing, is there a reason why that would happen if there was not a compound bound? I mean, what's the
I was not expecting this, so I didn't freeze any crystals that were APO. So I don't know if the APO was with the same conformation. But because we haven't seen this before on the other experiments, then I'm assuming it's compound related.
Okay.
At this point, yeah.
Okay.
Not DMSO at all.
No, because there is the same concentration of DMSO done in the XChem results. And yeah, and I couldn't see a DMSO molecule either. Yeah.
Right.
And then in the case of E. coli Mur here. So the crystals were super nice since the beginning. This is the condition in case anyone is interested, but the reproducibility was really low. So I was getting a 2% of the drops with crystals, which is really bad for XChem. I'm now in 15%. I need to check my last crystal plates. Hopefully that will be more. And I'm getting there. So at least we can have a decent reproducibility so I can do a first test on XChem. But yeah, so the experiment for soaking was the same. I soaked compounds at the same concentration as for the Mur E. And in this case, I tested APO crystals as well as incubation at different time points with DMSO. And then I included the AstraZeneca compound as well as the dual inhibitors and ATP. This soaking time is slightly different. So I collected different crystals at different time points up to 1 hour. So I got data sets for different time points for all of them. Now, what I observed during the soaking is that the crystals were looking where they were cracking all the time, except for the APO or the DMSO controls. So the compound seems to be doing something to the crystals. However, these crystals were still, even when they look cracked, they were still diffracting relatively good. So they were refracting at the same or in the same levels as the APO on DMSO controls. So it was quite nice to see. So in terms of diffraction, I think they are good for the XChem. on the, but then in terms of reproducibility, they need to get better. And then there's another issue that I would like to talk about. So this figure here is Mur E. coli. The structures are monomers in the asymmetric unit, but there is asymmetric related molecule nearby, and is making a nice little pocket in the crystal contact. And in that pocket, I was able to see partially one of the compounds. This is the ligand 759. And if we look at the structure, so that's the compound. So I can see this part, the part with the bromide, and I can see it at 50% occupancy. As you can see in this figure, there's a little nice pocket in there. And there is another pocket on the back as well. And if you look at the APO crystals and the DMSO crystals, there are also blobs appearing in this area, suggesting these two pockets might be pockets where compounds might be binding non-specifically in a crystallographic contact issue. So I think we should try to test this system with a partial XChem library and see if this is reproducible with different compound series, because if this is happening all the time, we're going to get a lot of hits in this area, then we will have to look into different packing, into different crystallization system. But yeah, so I do not believe this is the place for the binding of this compound at this stage.
Would this sort of binding also be responsible for the crystals apparently melting?
Yeah, so I think the melting might be because the crystals are binding where they're supposed to, and they're just melting the crystal, or also in the crystal contact as well, cracking it down. So yeah.
So that site that you're showing on the right there, that's a different site from where the original fragment was bound?
Yes. This is, in that, on the left-hand side, where all the original, all the schemes were basically hitting that area, not this one. Different area, different site.
Interesting.
Yeah. So that's basically it. There is not a confirmation of any of the binding. I think we should follow up the essays with competition essays to confirm that, if there is any binding to ATP site. Because if there is binding on the ATP site, then it makes sense. The co-crystallization experiments, maybe they do something.
Yeah.
I have started the co-crystallization experiments as well. So hopefully we'll get something.
Right. So 759, for which you found no ligand, is the one that was performing best in Becker's assay.
Yes, so that one, no ligand. Sorry, this was the 749.
Yeah.
The other one, I couldn't see it, but I saw the blobs of ethylene glycol, that is the cryoprotectant, and DMSO as well. I could see them floating around in between these two pockets.
Right.
Yeah, and for this compound, I cannot really see this area. This is nowhere to be found. It's moving a lot.
Right. Okay. I mean, the co-crystallization experiments are going to be important, and it's great you started those already.
Yeah. Especially if they are inducing a crystal conformational change in the case of E.
Yeah. Right. Okay, any other comments or questions from anybody?
I was wondering, Laura, rather than going into your SPR, unless people want to hear the SPR, perhaps it'd be good to go on to the enzymology to give people an update as to where we've got to, what we've assayed, and what the results are.
Yeah, exactly. Yeah.
We can always come back to that at the end, or at.
That's all right. Yeah.
Lovely, thank you. Adrian, do you think you first, then Anita? What do you think?
Okay. Right, I'll just share my screen. Right, can everyone see this?
Yep.
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 Right, okay. So what we're going to be talking about is our attempts to reconfigure the Mur Ligase assays that we do. So they'll work at much lower volumes and therefore be less of a drain on resources, for example, the substrates that we will have to make, and also to provide a fluorescence assay as well, which would allow that to happen. So the general idea is that, and this is exemplified on this slide by Mur-D, is that the conversion of UDP-Mernacala to UDP-Mernacala glue, dependent upon ATP and D-glutamate, generates per mole of substrate 1 mole of phosphate. And in the presence of inosine, pure nucleoside phosphorylase, that'll generate a mole of ribose 1-phosphate and hyperxanthine, which is a substrate for xanthine oxidase. Xanthine oxidase itself generates hydrogen peroxide, and hydrogen peroxide can be used by horseradish peroxidase, which in the presence of the chromogen and fluorogen amplex red generates resirufin with a fluorometric readout and a spectrophotometric readout. The fluorometric readout allowing reduction in the assay volume, in principle. So the development work that we've done for this has been done on a thermovarious flash, which and in spectrophotometric mode, both Pseudomonas aeruginosa Mur-D and Mur-E give distinct signals over and above the presence of the controls, they being the absence of the substrates, and give nice linearity with respect to added protein. The one thing I'm going to draw your attention to, because it becomes an issue later on, is the fact that ADP-CP, which is an ATP analog with a methylene interposed between the beta and the gamma phosphorus atoms, is a particularly good inhibitor of Mur-E, but is not really that effective against Mur-D. So spectrophotometrically, we have an assay that works on the various scan plate reader, and also incidentally in the Carey UV visible spectrophotometers we often use to establish whether an assay is going to work in principle. So fluorometrically, and I've shown the schemes for both Mur-E on the left and Mur-D on the right. The assay gives a clear fluorescent signal in continuous mode, again with dependence upon all the substrates in both for both Mur-E and Mur-D. And also, as far as Mur-E is concerned, ADP-CP is a very handy tool compound, which gives a very nice inhibitory response with an IC50 under the conditions we're using of around about 2.25 micromolar. These assays are done, have been done in a 20 microliter volume. However, we routinely run these continuous assays in a 10 microliter volume, and we now have assays that work continuously from Mur-D, Mur-E, Mur-C, and I also believe Mur-F, and they give nice linear responses to added protein. So far so good. Now, one of the problems that we've got is with a continuous assay, although from an enzymatic point of view, they really give perhaps the most accurate estimates of initial rate. As far as screening on scale is concerned, The problem that you generate is the amount of data that you have to handle. And therefore, HTS kind of really does depend upon stopped assays, which reduce the amount of data significantly. So in order to do this, and again, I've exemplified this with Mur-E, starting with a spectrophotometric assay with a defined response, which I have as this value 0.642 here, absorbance units after 15 minutes. If you run the assay where you basically miss out the inosine amplexator and the coupling enzymes, and you add 1 millimolar ADPCP to stop the reaction, and then you add the coupling enzymes back, you get a burst of absorbance over and above that you would see if you missed out the UDP substrate. The progress curves, once that has actually happened, are linear, although they slope upwards, but they are collinear, which is the point of this little insert down here. So we have the basis of a method, perhaps, which we could use to follow Mur ligase activity in a stopped assay. So we then translated that to a fluorescence assay in a 10 microliters volume on the various scan, and things do look a bit different. So you start the assay with the presence by the addition of diaminopimellic acid, the substrate. Around about 10 minutes later, you add ADPCP to stop the Mur-E reaction, and you simultaneously add the inosine. And then you basically look at the evolution of fluorescence in the complete assay, which is in purple, in the assay where you've missed out the DAP, which is in green here, and then in the assays where you've included ADPCP as an inhibitor. And HTS folks like to use this statistical parameter called the Z prime to calculate the validity of an assay, which basically relates standard deviations and means as a ratio, with a value greater than 0.5 being considered to be good. And you do get a Z prime at the apex, which it's about 0.68. But if you compare not just the full reaction against the interaction without the substrate, but the full reaction against the full reaction with the inhibitor, you have about 0.471. Now, the problem with this is that the assay signal isn't that stable. You can see it's beginning to decline quite rapidly at this point. So we're losing fluorescence over time. So that was something that we have to deal with. And we also characterized the window that we actually have to stop the Mur ligase reaction within. And essentially, if you stop the reaction after 5 minutes, you see very, very little signal. If you stop the reaction after 15 minutes, you see a far more abundant, prominent signal with clear discrimination between the absence in green and the presence of ADPCP, a stock inhibitor. This discrimination decays as the Mur ligase concentration increases, and you would expect that because even in the presence of an inhibitor, you're still accumulating product, and the longer you leave it at a higher concentration, the less discrimination between with and without inhibitor ensues. If you leave the reaction for 30 minutes, essentially you lose the window entirely. So what we have was a fairly user-unfriendly assay. We could define a Z prime, we could see it, but the parameters within which we had to work were quite tight. And if you talk to people like the European Lead Factory, they want stability of signal for at least half an hour. So what can we do? The other problem we've got as well is the fact that ADPCP is not a very good inhibitor of Mur ligases like Mur-D. Now, there may be some quite interesting structural enzymological questions about this because it's a very good inhibitor of Mur, but from a practical point of view, as you can see in this spectrophotometric trace, if you initiate an assay with D-glutamate and you try and stop it with ADP-CP, you get very, very little inhibition at all. So we looked at the reaction in more detail. So this is exemplified by Mur. So you have the potential to stop Mur reactivity with EDTA, which will chelate any magnesium requirement for ATP. You have the potential to try and stop the reaction after the Mur ligase step. So at the level of pure nucleoside phosphorylase with this compound, phorodazine, which is a transition state inhibitor of pure nucleoside phosphorylase, or allopurinol, which is an inhibitor of xanthine oxidase, or this compound, which I'll talk a bit about later, A33855, which is an inhibitor of horseradish peroxidase. So we investigated all of these. So EDTA as a stop, again, is not that effective in this particular assay. So this is a Mur assay. The black line is the assay that we've attempted to stop with EDTA. There is a water control. The drop in absorbance when we add the EDTA is simply because of the volume dilution when we add the inhibitor. But clearly there's no real purchase on inhibition over that you would see just by simple dilution. So EDTA wasn't going to work for us. Allopurinol, which is an inhibitor of mammalian xanthine oxidase, actually is turned over by the microbial xanthine oxidase we use here. So that wasn't going to work either. Phorodazine is a very tight binding inhibitor of purine nucleoside phosphorylase, and you can actually show this. You can look at the inhibition in related to phorodazine concentration, looking at PMP activity, and the IC50 basically tracks the PMP concentration in the assay. What this meant was that we would, because we were using PMP to accurately reflect Mur reactivity, because we were stopping the reaction after that point, we needed to add a fair amount of phorodazine to the assay. But in actual fact, when you treat an assay with phorodazine with the anticipation it would stop it, and this is Mur, ADP-CP proved to be considerably more effective than phorodazine itself. So that was another idea that went west. And finally, we come to A33855. This is a preparation. It's made by Thermo. It's marketed as an Amplex Red, Ultra Red stop reagent. I did inquire as to what is in it, and I got the expected response. I was told it was proprietary, and thank you, but that was that. However, in the assays that we use, this works very well. So with Mur-D, for example, you can follow the line in blue, where we attempt to stop the reaction with ADP-CP and it fails, or we add 10 microliters of this Mur A3385 and it stops it completely. You get the same response with Mur-E. In this particular panel, this is a Mur-E assay where I was attempting to stop the HRP with sodium azide, which clearly didn't work. But this material, A33855, again, it completely quenches the signal. And so this appeared to be an effective method for actually stopping the reaction. So in principle, we have an assay, a stopped assay that you could translate to the other ligases. So at the moment, we're attempting to trial this in assays, although at this present point in time, we do have some issues with the plate reader and some of the components. So this basically shows a stopped assay data set where we've looked at the fluorescence after 0 and 60 minutes after stopping the reaction with A33855 at 0 and 1 hour at 3 separate fluorescence wavelength sets. In this particular data set, the assay hasn't worked that well. What we think is going on is that inosine itself has a degree of instability. So we've been using stock solutions of inosine. I found literature which suggests that it very, very slowly breaks down to xanthine. So the bond between the nucleoside and the ribose ring and the base isn't infinitely stable. And if you generate xanthine, then your backgrounds go up. And in actual fact, these background values in the absence of DAP are far higher than the ones that I was presenting earlier. So it looks like there's been some decline in performance, but I'm fairly confident that we can reverse that. It's just a case of making sure that everything we use is fresh. And that really is where we are at the moment.
Good. Thank you, Adrian. That has been a tour de force for the Mur Ligase enzymology team for the last few months, and explains, for those who are wondering, why we haven't got it sorted already. Has anyone got any questions for Adrian?
Not a question, but a fantastic effort.
Thank you.
Good.
I'll send along. I mean, I guess the question I would have is, AstraZeneca ran a MURC high throughput screen. All the assay conditions are published. So I'm a little curious about, how that, or why that wasn't at least, thought about in terms of those assays that have already been kind of published, both, I guess, for MUR B and MUR C.
Well, there's a certain amount of pragmatism that goes around. So we've got experience using Amplex Red in other contexts, for example, with PBP transpeptidation assays. And in actual fact, I mean, as I often find, there's nothing new under the sun. The idea of using Amplex Red, HRP, xanthine oxidase, and PMP in combination was actually published for a HTS assay for MUR-A by GSK. So, given that that appeared to work and give decent data, given that we had the reagents in stock, we followed, if you like, the path of least resistance. And
Okay. All right.
pretty much almost got there.
We've run a 40,000, we worked up and ran a 40,000 compound MURC screen 15 years ago with MRCT, but the sensitivity wasn't that great.
Yeah. I think that was the other thing as well, which I brushed over. The sensitivity of this assay is about 5 times that of the MSG assay in terms of the spectrophotometric signal. There are ways in which you can double that by coupling the final product to uricase, which doubles the amount of Amplex Red product. And actually, if you titrate the phosphate product, you get an extinction coefficient getting on for 100,000. So, in principle, it could actually be quite useful.
So this was really focusing on trying to hit all the buttons for ELF for their parameters. That's why we did this, for miniaturization in particular, and the cost, because we were going to have to bear the cost of an ELF project. So miniaturization was absolutely essential, given that we haven't got any money for reagents. So that was super important why we did that. Saying that, as Adrian identified right at the beginning, we have super robust continuous assays. So that's probably a good point to introduce Anita's talk, who's going to talk about actually assaying some compounds.
Okay, I shall stop sharing.
Thanks, Adrian.
So I'm going to be speaking on the compound W, which we've been speaking about before, and also ADPCP and their inhibitory effect on various Mur ligases C, D, E, and F. Just to refresh for everybody, what I'm calling compound W is the AZ compound, which was then given another name WYH9. That's why we're just for short calling it compound W. And ADPCP is the compound that Adrian has been referring to, also known as AMPCP, 5-adenylyl methylene diphosphonate, which is a good Mur-E inhibitor. And we believe that compound W was a good Pseudomonas aeruginosa Mur-C inhibitor. So just to confirm that our assays were working and it miniaturized to 10 microliters as a fluorescence assay in a plate reader, I conducted these experiments, which just were a snapshot against Mur-C, Pseudomonas Mur-C. We just diluted the compound to 10 or tested it at 10 micromolar. And you can see that compared to a DMSO control, compound W is very inhibitory, so which confirmed previous reports. So it was good to see that we could reproduce that information. However, ADPCP, which is a good Mur-E inhibitor, is not very inhibitory against Pseudomonas Mur-C. We just also then wanted to have a look whether compound W is actually effective against strep pneumonia Mur-C, and it's only very slightly effective against the strep pneumonia Mur-C. So that was a bit unfortunate. So then we looked at compound W and ADPCP against the Pseudomonas Mur-D, E, and F ligases. And against Mur-D and Mur-F, there is no inhibition seen with compound W. But against Mur-E, we were observing some inhibition. It was quite promising. So just to summarize the percent inhibition that we have been determining, against Mur-C, we got 99% inhibition with a final concentration of 10 micromolar W. For the rest of the Mur ligases, we tested compound W at a concentration of 20 micromolar because we thought we'd give it a bit of a chance to work. And as we saw, Mur-E, we're seeing about 31% inhibition of Mur-E with 20 micromolar compound W. And ADPCP is quite effective against Mur-E at 20 micromolar of compound, 69% inhibition observed. So then we decided to do IC50s to get precise numbers of compound W against Mur-C and Mur-E. And against Mur-C, it's a nice low number of 1.2 micromolar, and it's 11.1 micromolar against Mur-E. Then, because we saw over here that, if I just take you back to that slide, that it had, the compound W demonstrated 31% inhibition against Mur-C, we were wondering whether if there was any synergy, if we added both compound W and ADPCP, and would it reduce the IC50 even further in the presence of Mur-E. And these are the results. So the IC50, as we saw before, of compound W with Mur-E is 11.1 micromolar. We had to test the IC50 of ADPCP, which was 2.3 micromolar. And when you combine the two, we managed to reduce the IC50 down to 1.3 micromolar. This particular experiment was conducted where compound W was present at its IC50 concentration of 11.1 micromolar, and then we determined the IC50 of ADPCP, which came down slightly from 2.3 micromolar to 1.3 micromolar. when we reversed the order and we had ADPCP present in the master mix at its IC50 concentration, we got what looked like a very random set of spots, and which we tested and retested, and we still kept on getting this. But if you have a look at the actual readings, they vary just only slightly between about 1,000 and 1,600 fluorescence intensity units per minute, which is actually very low level. So in effect, this is almost linear, really, which seemed to indicate that once ADPCP is present in the mix, no amount of W, well, there doesn't seem to be any effect of any added compound W to the mix is not going to increase the inhibition. So we were then wondering, because we got such different results when we added it in the other way, whereby compound W was in the master mix and then ADPCP was added at different concentrations, we wondered whether there was actually an order of, there was something related to the order of addition of these compounds to the master mix. So we did another experiment where on the one hand, we had compound W in the mix and then added ADPCP at different time points afterwards, either immediately after adding compound W or 5 minutes later or 15 minutes later, to see what effect there would be on the inhibition of Mur-E. And then with another set, we had ADPCP already in the master mix and then added compound W immediately after or 5 minutes later or 15 minutes later to give the enzyme more time to bind to the compounds. And that is the result that we got, which confirms the previous findings. So when compound W is added first, you can see that there is definitely a benefit of adding ADPCP to the mix. There is a further inhibition seen even as quickly as immediately afterwards. There's a reduction in activity. Whereas when you have ADPCP in the mix, compound W has no more further effect to the inhibition of Mur-C, which seems to imply that it binds really tightly to Mur-E. And just to illustrate the numbers in a different way, if we take that not having any ADPCP doesn't give you inhibition, you get an additional 50% inhibition if you add compound W to the mix, to the master mix at its IC50 concentration. So that's the work we've done so far.
Right, thanks, Anita. Does anyone have any thoughts or comments? I mean, it seemed to be particularly interesting that you were getting compound W hitting Mur-C and E, but not D.
There may be a relationship between that and the fact that ADPCP itself is a particularly good inhibitor of E, but really, really poor against D.
It certainly seems that way, doesn't it?
Yeah. The structural basis of which is presumably quite interesting.
So slightly different nucleoside binding pockets.
Yeah.
Laura, have you had any observations on thinking around those differences in binding pockets, or perhaps we ought to pull up some structures that
yeah, I did some analysis, but so it's in an area that is a loop, and we will need the same structures for the three of them, you know, ATP bound or analogs bound structures for mu, D, C, and E for the same organisms, and we can do proper comparisons, but they are not examples for the three of them on the same organism. So yeah, that's why I'm trying to get as well the E. coli, only ADP, and yeah, I'm trying to get that as well so we can understand that.
So remind me, because I can't remember, Do we have Pseudomonas C, D, and E with ATP or ADP bound into all of them?
No.
No. Which one's missing? Tell me, D.
Wait. Let me open my list.
This is Jan. I'm just working on the Pseudomonas Mur D structure with ADP. Yeah. I don't think we have anything else.
Okay.
Yeah, so you have C and D in Pseudomonas.
Yeah, but no, like the three of them is not. Pseudomonas, there is one missing, and then Acinetobacter is one missing as well. Mur E is missing for Acinetobacter, E. coli, and Pseudomonas.
I'm not aware if that is in the SSGCID pipeline, any of the Mur E. Do you guys know?
I don't know, but I requested it, and they are sending me some things next week or this week, depending on how it works. So I can follow up on that. They are also cloning E. coli as well, extra, like, yeah, the things that I don't have. So yeah, so hopefully we'll get that covered. Because it will be very interesting to know what was the reason for that to happen.
Yeah.
Right. Thanks, Anita.
That's all right.
Matt, over to you.
Well, we're running up against the hour. It's the only problem is the fascinating data. Thank you. Just wanted to make sure we have the chance for others to bring up things that they would like to draw people's attention to whilst we're in the meeting here. Laura, you've posted the SPR results already online.
Yes.
Did you want to speak to those very briefly in the last few minutes? Because obviously they're quite important. This is for the atomized compounds.
Yeah, so there are some, all right. So I got some KD data, and I don't know if you want me to share my
If you would like to, yeah, that would be great. Hang on a second.
So I'm just gonna go to the summary, result summary. So yeah, so we got some KD data for some of the compounds. They are indicated in this table. They are not super strong binders as we were expecting. This one looked to be the best one, but the signal is really weak, and there is some non-specific binding as well. So I think it's just a weak binder. It's overestimated KD. Some compounds are showing as well two binding sites. The second binding site could be a non-specific binding site, or could be relevant. That would need to be followed up with more experiments. I did some competition assays in the presence of AMPCP, and there are some compounds that showed no binding when the AED-PCP was bound, and these are the results summarized. One of them, I think the one that is looking more interesting is this one, the compound 212. It was high XChem heat. It has a negative binding response like the AD-PCP, and then it does not bind when the AD-PCP is binding, and it has, we can calculate KD values. So this one, I will, if it's possible, we should test them on an assay to see if it's indeed competing against, well, with ATP. And then, yeah, so that's, and then some compounds. For example, like this one is just one example that showed no binding to in the presence of AMPCP, but it's not an XChem here, it's new compounds that could be a potential competitor for AMPCP. I do think all these results need to be validated with the assays. So after we screen the library against the assays and do the follow-ups, I think this should be compared and see if we can trust this data. Therefore, these compounds that we flagged as potential competitors or new competitors could be moved forward, and maybe we can have extra chemistry for the future. But I don't think we should make many more conclusions until we don't have enzymatic data, because this is the first time we do SPR on these proteins.
And are the compounds due to go into the enzymatic assay? Just wanted to check that.
Yes.
Because some of them, yeah.
So this library will be screened
Okay.
on the assay.
Fantastic.
We will screen all of them. And then I will compare everything, what's happening and what makes sense, what doesn't make sense. So I can learn as well how these proteins behave on the SPR.
Okay. All right, great.
Yeah, it's just, that was the AMP-CP binding with negative binding. Yeah. If anyone has any questions on the SPR?
I don't have a question on the SPR, but I just wanted to point out, I guess, IC50s obviously depend on assay conditions, but so the data for, excuse me, the data for compound W in the Mur-C, Pseudomonas Mur-C assay, it's about 1,000 times less active than AstraZeneca reported. So just as a, I guess, a point to, I guess, for people to think about, it's like, how we want to think about those differences, I guess.
Yeah, I did not try the AstraZeneca compound on the SPR though.
I wasn't referring to the SPR. I was referring to the biochemical assays that Anita reported.
I think maybe our ATP concentration is different to what AstraZeneca used.
Yeah, I understand exactly. And so the question becomes then about, what conditions you're going to be using in screening, and how that impacts whether your hit finding and your output. That's all. I'm just saying there's this difference. It's a 1,000-fold difference. Those were I think I compound almost 7 nanomolar in the AstraZeneca assay, or at least 3 nanomolar or something like that. And you're reporting out like 1 micromolar. So it's a 1,000-fold difference. And just for awareness, okay, about that difference.
I think this basically comes down to the business about trying to use IC50s as comparators as compared to trying to use KIs for the same purpose. And that would probably be better off trying to actually do that to give us a better reflection or better ability to compare between different data sets, particularly when things are done in slightly different ways.
I totally agree, Adrian. I think it's more of a question about ultimately if you're running assays and you're trying to identify new hits, new series, new compounds, and how sensitive and how at what concentration you're running substrate, for example, and are you going to be competitive, and are you asking it too much of the compounds to do too much in terms of competition?
I think one thing is true. If I remember rightly, the IC50s that were being generated for C, I think were quite close, relatively close to the actual enzyme concentration. Under those circumstances, without changing the assay completely, it's difficult to be accurate about what the true comparative IC50 would be.
Good points. Well, we're out of time, I'm afraid. I just wanted to give Jan Jensen the chance to talk about the compounds he put up online just the other day, because they just very briefly, because they do look pretty interesting. They're all based on the same motif, as far as I can tell, that central ring system.
Yeah, so it's just to summarize. So this is basically a genetic algorithm that's trying to find binders with docking to Mur-C, where we focus on primary amines with fewer than 5 rotational bonds to sort of keep it in the cell. And so we've generated about 150 molecules, and I sort of went through them to try to do a quality check and also look at synthesizability. So this is the bound AstraZeneca compound. I think this is the W compound. So just to give you an idea of the interactions, I try to sort of match these interactions and looking for those in the dock process. So not really matching them, but looking for them. And so here is always the reference compound. So actually the code found one family of compounds with this ring here and this sort of moiety here. So being that we force it to have a primary amine, I think there's always going to be some salt bridges with the aspartate here. So that's in all the compounds. So I was focusing more here on whether we have some similar interactions here, and there is to the histidine and the asparagine, which is the same one here. And this one, of course, so I ran it through a retrosynthesis program. I'm not a synthetic chemist, but at least this program claims that this can be made in one step from purchasable compounds. Whether that's accurate or not, I don't know. Here's another one again with the similar moiety here. There's a lot of examples. This is just a slightly different synthesis. But basically the thing is the same, binding here with hydrogen bonds and here with a salt bridge and a hydrogen bond. Then I looked for other sort of binding motifs. So here you have this group here. Now you have 4 or 5 hydrogen bonds, depending on how you count. Same binding mode here with the primary amine. This can also be made from purchasable compounds in one step. And here's another slightly different sort of binding. Same spot all the time for the hydrogen bonds. These have more hydrogen bonds. Maybe that's more promising. I don't know. This is a more complicated synthesis, at least according to the retrosynthesis program. And also there's some retroselectivity issues here. So, but these are slightly updated slides, so I'll put them up and you can look at them at your leisure. Here's another binding mode, slightly more complicated. Only 2 hydrogen bonds here, but now it has this, there's actually 3 hydrogen bonds here. Now you're involved with tyrosine. And there's also this pi-pi interaction, which is seen in the AstraZeneca compound. But again, a more complicated synthesis. 3 more left. So another motif here. Now this looks a little different. That might be interesting. Then you have this one here. Again, this looks slightly different. Also a different synthetic route. So maybe one thing to consider is whether one can buy a lot of derivatives of this, using the same reaction to explore different compounds rapidly. So these are basically the best bets. So 8 or 7 compounds filtered down from 15. These are sort of our best shot at it. We also went through 250,000 compounds that you can buy from Enamine in their hit location. And actually only one of them sort of looks promising, maybe. That's this one here. So it has, it binds roughly in the same part of the pocket as this, with hydrogen bonds involving the same residues. And then it has, it's not a primary amine. We couldn't screen for that in the library, but it does have a salt bridge here. This protonation state maybe is a little unphysical, but it's sitting out, pointing out into the solvent, so it's not really key. So that's basically the best shots in terms of binding, similarity with the known binder and synthetic accessibility.
That's great. Thank you. We're going to take a look at the purchasability of these and their synthesizability, and we'll post an update.
Great, thanks.
That's great. All right. We're way over time. If anyone wants to mention anything else, please do. The issue here has the recent structures from SSGCID. And then we're grouped together on Yuhang's synthetic work, which we haven't had time to talk about yet, but he's posted an update. The Atomwise issue, that we're still looking at how these compounds bind, because we haven't been able to get anything back from Atomwise about whether or not they're surprised by the crystallography results. And this section is the one we've just been talking about. We haven't had time to talk about the ELF situation. I guess I can quickly address that, Chris, because we've been in touch with them. There's no more capacity to run an ELF screen, despite the beautiful enzymology that we all just saw. And they're asking whether we could support it financially, and they would be able to run the screen of the European Lead Factory library. But it's pretty expensive. So there's no immediate way that we can pay that. We were running by some companies the idea that we could perhaps ask them to run it for us, so partners of the European Lead Factory, and I guess those conversations are kind of ongoing. But it did make us wonder about the value of another big screen and how much we might get for the project in terms of the amount of money that it would take to run that screen. Joe, you brought up the idea of running a focused kinase library. Chris, you were going to look into the life arc compounds as another potential source of molecules. Did anybody want to address any of those issues?
Give you a 5-second update on life arc. Yes, they're keen to engage. They've got, they did very big fragment screen against E. coli, Mur D, and E, and have 25 fragments with sub-micromolar hits.
Can we access the data?
So that's 60 micromolar, I think. So they're just working that through the system. That they are also going to answer the question for us about the diversity of our original MUR-C kinase focused screen that we did with them 15 years ago. Against the enamine available kinase focus screen, because Joe was saying, well, perhaps we ought to look at the enamine kinase focus screen. So they're going to do the bioinformatics on the cheminformatics on that and get back to me as to how different enamine is now. That's good.
That would be very good. Do you think that, I mean, are they willing to share the data and to put that in the public domain?
Yes. They're just doing internal due diligence. So
okay.
Yeah, I think that can be positive.
Very good. That's very positive.
Can I just make one quick comment? When we have these presentations, people have codes for compounds and things like this. As a chemist, it would be quite nice if they had the structure with the presentation. Yeah,
I'm with you. We do need to worry about that, because I think that the compound W is not the compound you think it is. It's the compound that Yuhang made, which is like AZ5595, but not. So Yuhang's been busy making sure all his compounds have OSA codes, so the simple code, which is then constant. I think we need to start to be using that as a way of referring to compounds unambiguously. But yes, structures on slides would be awesome. Yeah.
We do then, because that will explain one potential difference in the data set between AZ IC50 and Yuan's compound W IC50, if that is a different.
Yeah, exactly.
It's still potent. It's still potent. There were several compounds in that paper that were potent, and Yuhang made one of them because it was a bit easier to get to. He's since made AZ5595 and can ship that.
Okay.
Yeah, but it should still be. I think
it was eight nanomolar, Chris, in the AC paper.
Yeah,
okay.
It's still good.
What you had, the compound W was 8 nanomolar in the AC paper.
Cool. Okay, I think I'm looking at it. We're going to have an internal discussion around our assays. We do pride ourselves on being able to prime them so they are sensitive. So I think there's some technical thing we need to just double check. They're not crap assays.
But, the only comment I would make is, you actually may be doing the right assay, and AZ may have been doing the wrong one. I mean, if you think about the potency that, Anita found, and the fact that these compounds, well, I mean, in the end, they didn't have wild type MICs, but they did have MICs when they were added with, I think, polymyxin or colistin, I can't remember which, in terms of permeabilizing the E. coli. So anyway, this is always a challenge. This issue about what conditions, as Adrian pointed out, and maybe there are other better ways to look at the data. But thanks for your efforts. I know this is a huge undertaking that you guys are doing, so it's greatly appreciated.
Okay, great. If there's nothing else, we can finish up, and I'll post the recording and update the issue.
Yeah.
Thanks.
Yeah, I think just one more thing. I guess I didn't post it quite clearly. Sorry about that, Joe. I think we need help with 2 more compounds to be docked. That's the main thing. We want to switch the core to a cheaper one, the purine core.
Yeah, I've looked at that. I'll talk to you about it offline, but there's an issue with that idea, unfortunately, but we can talk more about, that offline.
Great.
Okay, thanks. Thank you.
All right, thanks for your input, everyone. Thanks for the great presentations today from the Warwick team. That's really, really fantastic. All right, thanks so much. See you next time, and I guess we'll be in touch with everybody throughout.
Bye.
Thanks.
Bye.
Bye.
Bye, everyone.